as an example of how to do balancing of a redox reaction, I just wanted to do a relatively complicated question. It's not that hard once you get started, but it seems quite overwhelming to start with. So we've got hydrogen sulfide gas, so there it is, that has been bubbled through a solution of potassium permanganate. So there's our potassium permanganate solution that has been acidified with hydrochloric acid. So there's our hydrochloric acid aqueous. And then what you need to do is you need to get anything that can be ionized or dissociated into its ions. So obviously the gas can't be, but the potassium permanganate, there's the potassium ions, the permanganate ions, the hydrogen plus ions, and the chloride ions. Now, just reminding you that hydrogen ions obviously can be written as hydronium ions because that's essentially what it is. Hydrogen ions in the presence of water will give us hydronium ions. In this section, you will only ever speak about hydrogen ions though, but know that they are interchangeable. They are essentially the same thing. Hydrogen ions exist as hydronium ions, but just for the sake of, I guess, space saving on the SEP table, it's generally going to be as hydrogen ions. So there they are. There are 1, 2, 3, 4, 5 players, and now what we're going to do is find them on the SEP table and see how they relate to each other. So here's a copy of the SEP table. You can't see the whole thing, but we can see enough to see those our arrows to be able to see those trains. And so what we're going to do is, instead of circling things on the table that they can get quite messy if you've got to then erase them a little bit later, you're just going to grab a couple of pens, pencils, whatever you've got handy, and you're going to put the pen or pencil down wherever you see an ion that you were looking at from before. So we've got hydrogen sulfide gas, there it is. So I put the pen down next to it on the side that I see it. Then there was potassium ions, there they are up at the top. Then we've got permanganate ions, they're down at the bottom over there. Hydrogen ions on their own. So the hydrogen ions all over the place. You'll see if you look in some of the equations, they're hydrogen ions, and we'll circle back to that in a sec. But if we were looking for hydrogen ions on their own, that would be part of the SHE equation, and then chloride ions would be over there. So if I was looking for all those 5 players on their own on the table, this is where I would find them. And now you're literally just going to use your table as intended. So we're going to look at the substances that would be oxidized first, and we're going to use our table, which has got that arrow showing increasing reducing ability, so increasing ability to donate electrons. So between these two, which one is going to be better at donating electrons? The stronger reducing agent between these two would be the one closest to the top, so I take away this arrow. I'm going to take away that substance. Then on the left-hand side, where we've got the substances being reduced with increasing oxidizing ability as we go from the top down, looking at our arrow on the side there, we can see of these 3, which one is the strongest oxidizing agent. It's going to be the permanganate ion down there. So I take away those 2, and now I see that I'm left with those 2 substances. And because I can form a tick between the 2, or in a better way of speaking, I've got a strong oxidizing agent and a relatively good reducing agent, and that will result in a spontaneous reaction. So that means those are going to be our 2 key substances, and the others are obviously spectator ions or acidifying agents. So let's go and have a look at that then. Go back and write these down. Oops. So we're going to say our 2 substances that we are therefore then working with is the hydrogen sulfide and the permanganate ion. So the oxidation half reaction is going to be, and I'm reading off the table, my H2S goes to sulfur plus 2 hydrogen ions plus 2 electrons, and my reduction half reaction is going to be our permanganate, MnO4 minus, plus 8H plus 5 electrons goes to Mn2 plus 4 H2O. So I just read those straight off the table. So there's the hydrogen sulfide one. I read that one that way, obviously, because it was being oxidized. And there's the permanganate one. I read that one that way because that was being reduced. So in terms of what is being oxidized and what is being reduced, so this is the substance that is being oxidized. Our H2S is being oxidized, which makes it the reducing agent. And the permanganate is the substance that is being reduced, which makes it the oxidizing agent. Okay, so that then means we've got these other 3 substances. What are they there for? So they are spectator ions. So remember, spectator ions are going to be ions, specifically ions that do not take part in the reaction. Take part in the redox reaction. So they are only going to be there as in order to make up charge. So our spectator ions in this case are going to be the potassium ion and the chloride ion. So that hydrogen ion, we're saying, now why, what is happening there? If you look within our reagents, we've got H2S, we've got permanganate, and we've got hydrogen over there. So that means that hydrogen is actually taking part in the reaction. So it's not a spectator ion, it's doing another job. And in this case, it's an acidifying agent. So the hydrogen sulfide, anytime you see the word acidified, that's telling you that you've got hydrogen present, which is the same as having hydronium present, as we said. So there it is. There's the hydrogen ion, and that's going to be the acidifying agent. So you'll see that there are actually quite a few equations on the table that include hydrogen. So there's one, there's quite a few. So it's saying those reactions are not going to occur unless hydrogen is present as part of the reaction. Okay, so now we need to balance this, and remember that because redox is about transfer of electrons, all we have to do is balance the electrons. So between these two, we've got a lowest common denominator of 10, and so this reaction we're going to multiply by 5, and this reaction we're going to multiply by 2. Now at this point, I'm going to recommend that you rewrite this in rough so that you can scribble on it easily, so that if your examiners are trying to see what you've done in either of those steps, that you haven't now gone and scribbled over it and made it unreadable. So just take the 2 seconds to quickly write it out in rough. You'll see how quickly we'll go. So I'm going to multiply that 5 all the way through. So I get 5 H2S goes to 5 sulfurs plus 10 hydrogens plus 10 electrons. And my reduction is going to be my 2MnO4 minus plus 16H plus 10 electrons goes to 2Mn2 plus 8H2O. Okay, so now that's all multiplied through. Now, what I like to do is I like to go through and separate reactants and products. So on my arrow, I put a line through for the oxidation half reaction and for the reduction, and then I join them. So now you can see this is on the left, that's on the right. And then you cancel anything that can possibly be cancelled. So my electrons should cancel. If they don't, you've made a mistake. Go back and check your LCDs. So my electrons should cancel, and that tells me that everything else will be balanced. Then look for anything else that can cancel. You're looking for waters, hydrogen ions, hydroxide ions, any of those common substances. In this case, we've only got the hydrogen ions. So I've got 10 on the right and 16 on the left, so I'm going to cancel that, and I'm left with 6. So now when I come to write my net ionic equation, remember that for IB, they're not going to ask you to put spectator ions back in. They're only going to ask you to identify the spectator ions. I literally go through and write down everything on the left, going to everything on the right. So that gives me 5H2S plus 2MnO4 minus plus 6H plus now goes to 5 sulfurs plus 2Mn2 plus 8H2O. And we should probably put these phases in as well. That would be helpful. Okay, so that is how you would have worked out, or one way of working out that particular equation and getting that balanced net ionic equation.